I want to talk about the homework and what I did this week. Um, so this week, this homework, I want you to, sorry, I keep getting a million messages. I really wish I wasn't. Um, so this week, what I want is I want you to go through the homework 7. And if we go to it, if we go into assignments and we look at homework 7, I don't want you to worry about getting homework 7 right. What I want you to do is I chose 7 different interactive problems. I want you to try them, try to get them right, try to understand them. And if you get them wrong, no big deal. At the end of, so next Wednesday, I'm going to look, and if you've gone in and you at least tried them, you'll get full credit. At least you've tried some of them. So I can see that you went in, you tried answering some of them, and let's say you got a 0 on all of them. You'll still get full credit. What the idea here is that I want you to be okay getting stuff wrong, but trying to figure out what's going on, to play around it, and just don't worry so much about getting things right now. That being said, next Tuesday, we're going to do a whole bunch of problems on energy. And those ones you will have to get right on the homework, obviously. So I just want to help you really get down the concepts. And the reason why energy is so important is it's kind of always in the background. It's always in our tool bag of things that we can do. So if we look at a system, if you're a biologist and you look at a cell and you're trying to figure out what's going on with like proteins in a cell, you use energy. You set it up with energy and you try to understand the energy transfer. If you're an engineer, same thing. So it's really important that we understand how to deal with potential energy, kinetic energy, and work and things like that. So let me just show you these really fast, and then we'll get to the lab. When you go into the homework, it gives you this little story. Some of them have simulations, some of them don't. And then it asks you some questions. And you may not know how to answer these correctly. Just go through and try to figure it out. If you've read the book and watched the lecture, hopefully you'll have a good idea of what you should do. But then you can usually play around with these simulations and it'll show you maybe something cool, maybe something just kind of this one's showing the work done on a rocket sled if the force is at 30 degrees. And it asks you a couple questions like which ones of these forces are responsible for changing the kinetic energy. So hopefully that'll help you kind of nail down that. The second question doesn't have a simulation, but what I really, really need to make sure that you understand, I'm going to write it right here, is for this problem, basically you have an object that starts at the ground with some initial velocity, and it reaches some point with a final velocity. And the kinetic energy of a particle is mv squared over 2. The potential energy is mgh. And what we do is this is actually the work of gravity. This is the change of kinetic energy, and work is change of kinetic energy. So what we really are looking at here is mv final squared over 2 minus mv initial squared over 2 is equal to mgh1, or initial, minus mgh final. What this really means though is it's mg change of h with a negative sign out front. Change of h is h final minus h initial. Now what that means is that we could actually choose h to equal 0 anywhere we want, and then all we care about is the change. But here's the main super important thing. Energy is really simple because energy, we can, by conservation of energy, we can write down E initial as E final. And then all we have to do is, we don't even have to think. MV initial squared plus MGH initial, we just write the types of energy. And we choose the initial and the final point to be somewhere relevant to the problem, right? But just know that in the background, what you're looking at is the change in potential energy is equal to the change in kinetic energy. And that, in practice, all you do is write down kinetic energy and potential energy. at initial, potential energy at final, and kinetic energy, or kinetic energy at final and potential. And that's all you do in energy. There's so much going on in the background that I need to really make sure you understand. And I don't want you to just kind of try to memorize this equation. I really do want you to know where it comes from and why it matters. So for this problem, it tells you like how high this building is, and that when it reaches the top, it has 0 velocity. So you can choose the bottom to be 0 height, the top to be 10 times the height of the floor, so 37.5 meters. And it gives you M, but you don't need it. The M's cancel. And you just need to find the work done. Well, the work done is the change in kinetic energy. So yeah, you do need M. I'm sorry. And you can find that by finding the change in potential energy as well. mg change of h with a negative sign. So essentially, you can play with these questions and don't worry about getting them right. I would say that this question is kind of the hardest question to do. It asks you, or it asks you, sorry, I can't talk today, what the form of, for work, what is the dependence on t? This is a parabola, so, or a quadratic, so it's t squared, just when you try to do this. 4 is really cool, and I really want you to play with it. 4 is basically making sure you understand that, can you make sure your mics are off, Brandon and Hassan? I don't mean to call you out,
I'm so sorry, I didn't realize that was on.
So this problem, what we're looking at is that the path is independent of the height. The height gives you the change in potential energy, but the path doesn't matter. So this is just kind of making sure that you understand the work is done in the direction of the force. And any work done that's not in the direction of the force, that's perpendicular to the force, doesn't count. It does no work. So it's path independent, although it does depend on the change of height. Okay. And then 5 is a simulation of 3 beads. And this one I actually really like. It gives you the kinetic energy and the mechanical energy. Mechanical energy is the potential energy from gravity and the kinetic energy added together. So this bead is going to go straight across, and its potential energy of gravity, mgh, is never going to change. Mgy, I should say. This bead is going to go up, so it's actually going to lose some kinetic energy because of the change of height. This bead's going to fall. Gravity's going to do positive work on it because it's falling in the direction of gravity. And it's going to gain some mechanical energy, or technically it's going to gain kinetic. So you can figure out which one would win. And when you do the simulation, it shows you which bead wins, and it gives you this nice little graph of kind of their energies. So it's a pretty nice simulation to hopefully help you nail down the idea that the change in potential energy results in it. If it's a negative change, results in an increase of kinetic energy, and how the work is done by gravity, I hope. 6 is a test facility of a rocket. It's just friction on a rocket and how it slows it down. Rocket car, I guess. And then 7 is a toy elevator with friction. And in 7, you can include graphs, and it kind of shows you what happens with the work, external energy, mechanical energy, kinetic energy, blah, blah, blah. So what I want you to do is I want you to just go through homework 7, answer what you can, try to get them right if you can. If you can't, at least answer them so that it shows up in Canvas that you got a 0. If you don't open it at all, I see a line, meaning that you have no grade. If you have a grade of 0 or better by Tuesday at midnight, I'll give you the full credit for this. I want you to play around with it without feeling like you have to get it right. Just learn as much as you can about this stuff, okay? Next week, we're going to have hard questions on energy. So we're not ignoring energy, we're just, I'm really trying to make sure you have a good base of knowledge for energy, okay? Is there any questions about that? If there are, please just turn on your mic and shout at me. If not, So in our modules, and I need to tell you guys this, in our modules, in the labs, I posted, as always, a lab handout as a doc and a lab handout as a PDF. The reason why I do that is some of you, if you have a weird, shouldn't say weird, if your Microsoft Word is different than mine, occasionally it won't display the equations correctly, and the PDF will. So I'm going to go through this. What we're trying to do in this, and I guess I'll just explain first of all what I did and what you can do or not do. So the idea here was I took a board. I had a board that was relatively flat and frictionless that was 120 meters long. And I used some books, and I couldn't find my protractor. I think I gave it to my kid. So I couldn't use a protractor, but then I realized, oh, I don't need one. I can take a ruler and I can measure this height as my Y and this distance as my X. And I can find, using tan theta is Y over X, I can find what this angle is. That's arctan, tan minus 1, or arctan, whichever one you want to say. Okay, but once I have this arranged, I put the IOLab on top, I put on the wheel sensor, and I let it go from rest. So V initial is 0, and V final at the bottom is obviously something. It'll be negative, because the IOLab, as long as you put where the little force eye bolt goes, if you put that downward, it will read it as a negative velocity, which is kind of what I want. We already know from incline plane problems that if there's no friction, no other forces, we have a free body diagram that is the normal mg cos, cos theta, and the weight down is mg sine theta, and we're saying that positive is up. So A ends up being, MA ends up being mg sine theta, or A ends up being g sine theta. Now, we know from constant acceleration that V final is equal to V initial plus AT. Assuming we start from rest, we get that A is V final over T, okay? But A is, if we look at this, canceling the M's, we get G sine theta. G sine theta. Now, I don't remember if we had this already, and I think we did in free fall, but the small angle approximation says that sine of theta is approximately theta as long as angles are small. We're just going to assume they are. They're not really small enough to totally assume this. But if that were true, then what we could do is we could solve for our quote unquote G here by putting V final over T is G theta, or G, experimental G, will be V final over theta T. Theta has to be in radians in this problem, okay? Because it's in here. If it were degrees, it's not in the proper units. So what I did was I set this up, and I measured X, I measured Y, and then I let it roll down. And then I added some height, and I did this for 4 angles. Starting at about 5 degrees, then 10, then 15, then 20. Okay, and I got data. And if you go into the lab handout, at the very end, so you can either use your IOLab if you want, if someone in the group wants to do it, get a nice board or something long enough that you can roll it down. But what I did was I actually covered my board in some aluminum foil to make it as frictionless as I could. And I put a pillow at the bottom. So this thing starts at the top and it slides down. And what it's doing is it's starting from 0 here, and then it hit the pillow. And that pushed it backwards, and then it slid back down again. So it kind of bounced at the bottom. And I've given you these 4 charts that I made of my data. It gives you the angle in radians, it gives you X, and it gives you Y for the particular experiment. The other thing you need from this graph, and the only thing you need from this graph, is you need the V here. That's the V final where I put the line. And you need the T. we're not going to do the uncertainty the way we did it before with the standard deviation and all that stuff. We're going to actually assume that we had a clock that read this time as our final time, that we started at 0, so this was the time that I have highlighted, and that we had a sensor that measured our V final as this value. So for each one, you're going to have X and Y, a theta, V final, and time. And I have all 4 of them. And you can see that this is actually the smallest angle. This was actually around 5 degrees, I believe. This was like 10, 15, and 20. So here's the deal. You can either do it yourself, and it'd be great if you did it yourself. But if you do it yourself, try to make it frictionless as possible. But I don't want you to have to find a board that's long enough to get good data. And if it's like trying to roll it down a book, doesn't really work. But if you do, you'll need to measure X and Y, and you'll need to take 4 readings at about 5, 10, 15, and 20 degrees, convert those into radians. If you've forgotten, there are pi, rad in 180 degrees. So 5 degrees times pi, 5 pi over 180 is 5 pi divided by 180 is about 0.087. So it's actually, mine's actually a little bit bigger than that. Maybe it was like 7. Yeah, I must have been around 7 degrees or something. But so just make sure that you note your X, your Y, your angle in radians. If you want to use a protractor, that's fine. But I really want you to find the angle by X and Y, and we'll talk about that in a minute. So this is our theory, and we already know this. I already just went over it. What we're trying to do here is we're trying to, once again, find the value of G where you are, okay? So we're finding an experimental acceleration due to gravity using an inclined plane that's virtually frictionless. Okay, so once we've done that, you can go down, and like I said, you can fill this chart out using my data. And if you use my data, I will say this, even though they're not written particularly well. Using my data, the experimental X and the experimental Y, because I used a meter stick, they're 0.5 or 0.05 centimeters. They're half a millimeter. If you use something else, it is whatever it is. So go, and for each of these 4, write down the X value plus or minus 0.05 centimeters, the Y value, and then the angle. This, however, you're going to have to compute. So when you get to calculations, you're going to compute this. Don't use half a degree. Don't use any of that. I want you to do this for a very important reason. There's a function that we almost never take the derivative of, and maybe you'll learn it in this one. So once you've done that, again, write the theta. These are just to make sure that you know which values these pertain to. You'll go down here, and for, say, theta 0.135 rad, write V and write T. But notice V, if you look, and I know it's really small, V here is negative. So V final for this one is negative 1.278 meters per second. What is the uncertainty? What is delta V here? This 8 is our smallest digit. So our least digit is 0.001 meters per second. Half of this is basically our resolution. This is our resolution, not basically. So half of that is our uncertainty of our measurement. And that's all you need for delta V. Time, on the other hand, yeah, Eric, you don't have to do it on your own. You can use my data if you want, but if you want to do it on your own, it's kind of fun to do. It's also kind of a pain. It took me quite a while to get it working decently. Okay, so, and then T here, if we look at T right here, is 1.43191. Sometimes, for whatever reason, the IOLab like cuts this off and just gives you zeros. If it does, ignore those and use this. But delta t is again half this resolution. So half of that is plus or minus 0.000005 seconds. 5 to the minus 6, 5 times 10 to the minus 6 seconds is your delta t. Okay, this is what you would normally do with any. So for V, it will be the same uncertainty for each time. But you will have to calculate the delta theta, and I'll show you how to do that for each angle, because that involves actually kind of an iffy thing. So once we do that, once you have this data, and this is what you would actually do, like let's say you're out doing an experiment in the field, you would just write down your uncertainties as half the resolution of whatever your watch, your voltmeter, whatever you have. So we're going to pretend like this was a sensor that we were reading the numbers right off of, okay? All right, so now that we've done that, you've got, in this, you wrote down your X and Y and your theta and your deltas. We need delta theta. Now this gets a little weird. So in order to find delta theta, it's not as simple as half a degree, because we're using arctan of y over x to find our angles in radians. So in order to do this, this is how we find the error associated with anything. We take the partial of the function with respect to each variable, square it, add them together. So here's the thing though. A lot of you may not have ever had to do the derivative of the arctangent, the tan inverse function. That is actually 1 over 1 plus x squared, where x is your argument. You also have to do the chain rule, which means you take that and multiply it by the derivative of the bottom. So what do you end up with? And then you have to multiply it by the delta over the actual function. What you end up with here is, let's say x was 120 and y was 40. You put 40 over 120 squared, 1 plus 40 over 1, or this is actually flipped. So just know this, these are flipped, and I'm so sorry about that. These should be y over x's. So yeah, please correct it. Y over x, I don't know, I just flipped them. So this would be like 40 over 120 squared plus 1 plus 40 over 120 squared, all under in the denominator, times delta x. Delta x is 0.01 or 0.05 centimeters. Theta is in radians. Take that whole thing, it's got a negative sign because of the derivative square. These will end up being like something like 10 to the, or 1 times 10 to the minus 6, so 1 times 10 to the minus 3. They'll be really small, which is great. But this is actually how we do the uncertainty if you ever wanted to do it mathematically. And I do want you to do those for these 4 thetas that either I found down here, or that you find on your own. So don't use the resolution of like a protractor. Then, so show the calculation of theta, it's just arctan of y over x. Show the calculation of uncertainty for the first trial. So in the calculation section, all you have to do is leave this, copy paste it into your lab report, grab this and copy it again, and then plug in your numbers for y and x and y over x and delta x and theta for trial 1. You're going to need to compute it for all 4 of them, but you just need to show it in the calculations. Think of it as like you're just showing me how you got that answer for the first one, and then I believe that that's the correct thing that you did. Okay. The next thing I want you to do is calculate the acceleration magnitude of the first trial. Don't be surprised if this is really different from what you're going to get for your graph, and you'll see that in a second. But so A is V final theta in radians times t. This will end up being like 6.6 or something meters per second squared, negative. and then show the calculation of the percent uncertainty from that first trial. This is just delta A over delta V. If you follow my math, you see it's right here. Delta V is that uncertainty you got from taking half the resolution, so 0.0005 meters per second. This was 5 times 10 to the minus 6 seconds for time, and wherever I put them. And for theta, it's the delta theta that you found up here. Okay, and just show this for the first one. But that's how you get your acceleration percent uncertainties. I do want those on the graph as a percentage. Since they're a percentage, multiply them by 100%. The next step, though, is I want you to take your 4 values of V, and your 4 values are theta times T. So it's not V versus T, it's V versus theta times T. Because as we said, our experimental is V final over theta T. In order to get this constant, we would need to have Y be V final, have X be theta times T. Set up a linear trend line, and that will give us a slope of the acceleration, the experimental acceleration we want. So graph velocity versus theta times time. Theta times time is on your X, velocity is on your Y in Excel. Linear trend line, make sure it has a title that says something like incline plane experiment. Axis labels, V is in meters per second. Theta times time is radian seconds. Make sure they have units. And then display the equation and the R squared value. Your R squared value, at least for me, wasn't very good. It was like 0.97. But make sure that you include this graph, and I probably should have talked about the graph before the calculations. But when you have a linear trend line, the linear trend line is Y. So for us, the linear trend line is mx plus b, where this is the intercept, the y-intercept if x is 0. And x is whatever. But this slope here for us is our experimental g, or what I'm calling a. Okay? And we can see that what we get is we get y plus b over, or sorry, y minus b over x is our slope. We're assuming that experimentally b would be 0. So our slope would just be b final over theta times t. When you get your trend line equation though, so whatever is on the term with the variable, that is your experimental g. And it will be close, at least for my data, it's like 9.5 or something. But do not let it pass through 0. We want b to actually have a value because it's a measure of our error, at least it's a measure of our systematic error. Now, is this great? No, we have 4 data points. Our systematic error and random error are probably all combined. If you had 1,000,000 data points, all your random error would die, and everything in B would be legitimately systematic error. Error that's there because your ruler isn't right, or you were measuring something weird, or just something weird is happening. Okay. So once you have that graph, perform these, get your slope A, take 9.8 meters per second squared minus whatever your slope is. This is a minus. Take this as the magnitude of your A, right? We don't want, well, it doesn't really matter because take this as an absolute value. Just make sure if A is negative, G is also negative, so that you're not adding these two because of signs. Now, in the questions, we'll come back to this for in a second. But I just want the percent error. I want to know how close your slope was to 9.8 meters per second squared. Fill out this table. Notice there's the trend line. I want the coefficient in front of the variable and the y-intercept here. And then I want your experimental g, which is your slope. And I want the percent error between these two. And then obviously I want your data points. You're going to need them anyway in order to graph it. So, and the delta A for each one, okay? Now, I'm assuming everyone has that, but that's not too hard. I hope it's not too hard. So that leaves us with the questions. And the questions are somewhat easy, except for the first two. So I'm going to talk about 3, 4, and 5 first. Independent variables are variables that the researcher or experimenter chooses. We are choosing that theta is whatever it happens to be for each trial. We chose that. You could also say we chose the mass of the IOLAB, or we chose the coefficient of friction of the surface to be 0. But in general, what we're doing is we're choosing V initial 0, and we're choosing theta for each experiment. The fixed variable is a variable that you cannot change, that does not change. No matter what you do, it should not change. The only fixed variable in this is really technically G. You could say the mass of the IOLAB, but you could change the mass really easily. What you can't change is gravity. Gravity is 9.8. It is fixed, right? Or at least it might be 9.8 where you are. Dependent variables, easiest to remember, the dependent variables are the ones that we measure. So we measured V final and we measured T, okay? But then this part. So we're assuming that this thing was frictionless. And I ask you, in one, I want a free body diagram if there were friction. And I want you to use A and solve for G. So what I want is this. I want you to say, okay, if this thing's going down, V, the free body diagram is N and mg cos theta, and there's a weight, mg sine theta. And there's friction. If V is headed that way, there's friction going this way that's mu n. And we're going to assume that up the incline is positive. It doesn't really matter though. So what we get from this is we get MAY is 0 is equal to n minus mg cos theta. That tells us that n is mg cos theta. And we get that MAX is mg sine theta minus mu n, which is mg cos theta. Kill all these m's, and what you get is you get A is g sine theta minus mu g cos theta, okay? Or what you get is that this is A minus g sine theta over g sine theta. Sorry, I have that flipped. I get that mu g cos theta is g sine theta minus A, or that mu is sine theta, you can leave the g there if you want, minus A over g cos theta, okay? That is the value that you're going to need to find, because I want you to solve for the coefficient. Then I want you to assume that there's friction, and this is where things get a little bit weird. So you're going to assume that your experimental G, okay, let's say I got 9.1 meters per second with a minus. I want you to find what the acceleration due to friction is. And what that means is the acceleration due to friction is G theoretical minus G experimental. So in this case, this would be minus 9.8 minus a minus 9.1, or it would be basically minus 0.7 meters per second squared. That's A of friction. That's how much of A. That is actually G sine theta, okay? If you look here, that is your G, I'm sorry, that is your A, not your G sine theta. G sine theta minus your A, okay, over G cos theta will give you the coefficient of it, okay? So once you do that, once you determine this A from this stuff, you can find this. I believe, did I do that right? I did the math this morning and I'm Nope. G minus A is mu G cos Y. Oh, yeah, because I'm see, I felt I was doing it weirdly wrong. So the force of friction is ma of friction is mu mg cos theta. Cancel this. A of friction is mg cos theta, and A of friction is also equal to 9.8 with a minus sign meters per second squared minus your G theoretical or your G experimental. That's what I meant. It felt wrong, like I shouldn't have had that sign there. So this being the case, that means that mu G cos theta is equal to minus 9.8 meters per second squared minus G experimental, or mu is this stuff, minus 9.8 meters per second squared minus G experimental from your graph over G cos theta. Now you might say, well, what theta do I use here? Go ahead and use the last one, the one for the steepest angle, okay? What actually is going on here, what I found and what actually kept me up really late last night trying to figure out how to do something useful with this. And before I say that, follow this math right here, where this is your A from your slope, okay? This is A from your slope. This is 9.8. And use A for the highest angle, the first trial here. But what actually I found when I did this was the friction was not even close to following mu times n. It was actually varying based on speed and angle. I'm not sure which, whether the angle mattered the most or the speed, but the coefficient of friction was actually going down the greater the angle I had. So having that the force is mu times mg cos theta actually is not correct. It's not even close to being fine. Hang on one second. So what I found was that mu was not a constant. It depended on some factor that I couldn't figure out, okay? So I just want you to treat it as a constant and solve for it for the steepest angle, which is this first one, where radians are 0.340. Okay, hopefully that makes sense. If it doesn't, shoot me a text and we'll go over it again. But remember, this is 9.8. This is whatever A you get from your slope. And this is 0.340 radians. Okay. All right. So, and your mu should be like 0.31 or 34 or something weird like that. So finally, so that's all I want you to do here. Oh, I'm sorry. I also want you to do it for the smallest angle. And I ask, is the value constant? It's not constant. It actually depends on either the angle or the velocity, or maybe the velocity squared. So I just want you to explain what you think is happening. Why would the constant of friction be different when the angle is steeper and the velocity is faster? There's no right answer there of what you think is happening. Just kind of justify it for me. Really kind of think about what may be happening. There also is another thing that could be happening there that you might realize. You would think that the cart is basically going faster, so there's more air resistance. So there'd be more friction the faster it went. Why is there not more air resistance if it goes faster? What I honestly think is that the faster it goes, the easier the wheels spin, the less friction there is in the axles on the wheels of the IOLab. But check it out. find the coefficient of friction for the highest angle and the lowest angle, and just tell me what they are, and then tell me why you think they're different. Okay. And I did give you the math if you needed it, and then I messed it up when I was talking a minute ago. So, all right. Finally, in your conclusion, as with all conclusions, I want it essay style, meaning I want paragraphs. They don't have to be long. They can be a couple sentences, but they need to address a couple things. What you found for the acceleration of gravity from your graph. What was your experimental gravity, the slope of your graph? And the percent error of that slope versus 9.8 meters per second squared. And then how accurate was this experiment? So what I mean there is I'm just saying, was it close? Did you almost get 9.8? You'll actually see that friction really didn't seem to play a huge role in this. It gets pretty good data, actually. The ILab actually rolls pretty smooth. I just didn't want to take a video of it and record it on my phone and then transfer it to you guys. If you want to try it, even on like a semi rough surface, it feels like the wheels actually don't have a lot of friction. And then state your uncertainties for theta and the experimental acceleration. So what I'm saying is state these delta thetas here and state these delta A's, these other delta A's, and your R squared value, and the y-intercept. Those are all your errors. So look at those errors and see if any of them are really big, right? And obviously compare your R squared value to 0.99. It'll be a little bit off, but anything less than 0.99 is unfortunately not very good agreement with your data. We only have 4 data points. Of course, R squared is probably bad, unless they were all on a perfect line. It's just too few data points for our trend line to really fit well what's going on. R squared is, again, a measure of how far off the trend line your data lies. Are these errors small enough to claim your experiment is accurate? And they probably are. If they're significantly smaller than any of your variables, if like the time is in seconds, but the uncertainty of time was 10 to the minus 6, yeah, this is probably a pretty good experiment for determining G. What kind of error is there? Systematic and random. There's air resistance. There's friction in the wheels or on the surface, okay? There's a little bit of lag maybe. There's measurement error due to the rulers. There's probably something I haven't even thought of. Maybe the ramp wasn't completely level. There's just all sorts of errors that you could probably think of that might have contributed to our error in this. Try to identify them as random or systematic. If I ran this thing 100 times down a ramp, then any error in the roughness of the surface shouldn't matter. What should matter is if it does have the same dip, then that would be systematic. If my ruler wasn't quite accurate, that would be systematic. Air resistance would probably be random, although it may be systematic if you think that the air resistance is the same every time. It's really up to you. And then how might you improve this? Now, obviously, the big one, do it 100 times for each angle. But other ways might be like use ice cubes, like blocks of ice on ice, so that there's literally no friction. Or maybe like an air, they have ramps that have air in them, and you can kind of like use like an air table and let them slide so that they ride a current of air down. Stuff like that. Oh, the last thing I should say. One thing about this experiment, every experiment we do, the acceleration due to gravity depends on a lot of things, and we're going to find that out in chapter 13. It depends on the density of the Earth below you, specifically any real big variations of density right below you. That's how you find oil way out in the middle of the ocean as you look at the gravity variations. It depends on how high up you are. If you go to Denver and you're a mile high, or Albuquerque and you're a mile high, gravity's different than here in Irvine or in Death Valley. So we're assuming that our theoretical is 9.8 and we found it was 9.5. Well, maybe gravity where you are is 9.5. You might want to mention that. You have no way of knowing for sure what gravity is. You could find it from a different experiment maybe, but just know that. So all in all, I think you can probably get this done pretty fast. You can use my tables if you want. If you want to go crazy and get some ramps, even get real nice long ones that you could maybe do in a room or your kitchen or something, do it. I would love for you to do it. But I know that not everyone has meter sticks and not everyone has a ramp and not everyone has, you know, everything that they would need to do this in a way that's pretty useful. So if your group wants to do it from my data, that's perfectly fine. If you guys want to try and do it with your own ramps, all I will say is that if you try to do it on your own, make sure put a pillow at the bottom so that it won't break, it won't go flying off the ramp. And when you look at the data, highlight it from where the velocity begins to change to where it spikes the other way when it hits the pillow. So what we want is we want the final velocity and we want the time from rest to final velocity. This data actually looks like I just copied it and it's all different. Like the ILab actually did a pretty good job, pretty smooth job rolling down. These little things are from where I turned and set it on the thing while I was taking data. But these are really quite smooth, which leads me to believe that the aluminum foil actually helped to get rid of friction. But really, I don't envision this taking you guys much more than maybe half hour to an hour for each part, each of you doing your part. The last thing I want to say is I may or may not, I'm trying to decide, I may move Lab 8 up. Lab 8, what we're going to do is we're going to look at scientific papers, and I'm going to have you basically talk about these things. Essentially, what we're going to do is have a very short 5-slide PowerPoint that basically talks about the conclusion. The idea behind it is that I want you to see how scientific papers are written and really get a feel for what we're trying to emulate with our lab reports. So that when you go to 4B and 4C, or you go to, you know, UC Santa Barbara, or you transfer to Yale, and they want to know if you know how to write a lab report. I want you to write a lab report that looks like a scientific paper, a short one. And what we're going to do is we're going to go on archive. And you're just going to look at the paper. I don't care if you don't understand the science. I just want you to give the gist. I'm going to want you to talk about basically 1 or 2 equations that they used. You don't have to understand those equations if they're really complicated differentials, but just say, yeah, this is what they did. This is the equation they used to get their data. And then there's a little bit about, like, what did they say was the problem? What did they say they would do next time? Or what did they think people should do? And you guys are going to do that as a group. You're going to choose a paper, and you'll do it, and it'll be a 5-minute. And I really want you in groups of 3. So if you don't have groups, you can obviously still turn this in as a 1-person group. I don't care. But if you don't have a group, I really want you in groups for those. Have somebody maybe find the paper, have somebody maybe do the PowerPoint, and then have someone talk. Or maybe all of you do it and each of you handles 1 or 2 slides. I don't really care. The point isn't to tax your brain and make you understand some crazy physics paper. It's to make sure that you see exactly what we're doing with lab reports, okay? So that's all I have. Remember, tomorrow by 3, your exams will be graded, your grade will be posted. If you do bad on it, don't worry. We'll talk about how you can do corrections and get back half the points you lost. Do the homework for me. For those of you that joined late, on the homework, what I want you to do on the homework is I want you to just try it. Even if you only have like 5 minutes to do it, just enter a wrong answer for the first question on each of the 7. You'll get the full credit for it. But what I really want you to do is just try them, get stuff wrong, really get down the concepts of potential energy, kinetic energy, work, and play with those sims. I think simulations are really good. The graphs of the energy are really good. And then, as I said, next week, we're really going to have real energy problems. These are just kind of quick conceptual problems, but we'll have real energy ones that we need to do some calculations that are semi more difficult. Okay, so I hope you all have a good weekend. If you felt like you were behind up to this point, really put some effort into this homework, knowing that you can't get it wrong. Just try to learn as much as you can. Watch my video. Hopefully this lab won't take up too much of your time. I know you all have a bunch of other classes to do. And then next week, we're going to go over problems, and we're going to talk about chapter 9. Chapter 9 is easier than energy, but it's a lot more problems that we can do with it. It's momentum. So please, if you also have time, read chapter 9, maybe. But anyway, unless you guys have questions, I'm all good. This is all I have for you today. I hope it all made sense. And thanks.
Thank you so much, Professor. Have a wonderful day.
I'll be really interested to see if anybody actually does try to make their own ramps. That would be cool. Hope it works out. But it was a headache for me. Anyway, talk to you all later. Good one.
Thank you, Professor.
Guys, girls.